All right. So a couple of things before we start. First and foremost, the study guide for Unit 3, which you guys will have time to work on in class tomorrow, is currently posted. It is not on Pearson. It is on Schoology this time around. So that is in the Unit 3 folder. Same deal as per usual, where the study guide will be a homework grade, and also I will take 5% of whatever you score on the study guide, rounded, and added to your test score as well as bonus points. So making sure that we are aware that that is on our radar. Hopefully also on our radar, perhaps more pertinently, is the fact that we have a test on Wednesday. Tomorrow will be a review day for that test, but also wanting to highlight for you guys, I am no longer going to be accepting grade submissions after Wednesday. So if you have any kind of outstanding work, if you have any assessments that are missing, anything like that, then all of that needs to be made up by Wednesday. And if you need me to, if you need to come in here during seminar or during my tutoring time, which will be tomorrow from 2:45 to 3:45, then you're welcome to show up. But if you need me to send an email to your seminar teacher, just please let me know by second so that I can shoot them an email either tomorrow or the day after to let them know that I will need you in here. So making sure that we are keeping track of what all we have to do and all of that. So where we left off, we were looking at our sequences here. So we had our just general definition for a sequence. That was like our just ordered list of numbers. And we said, okay, that's great and all, but really what we want to focus on are our like specific types of sequences that have patterns. So we looked at arithmetic sequences, which were those sequences with addition patterns. We looked at geometric sequences with multiplication patterns as well. Couple of points that I want to remind ourselves of kind of going into today as we start to kind of build up some equations around these sequences. First and foremost, when I am plugging a value in, so we talked about how sequences are really like functions. They are all functions. When I plug a value into my function that represents a sequence, what does the input kind of represent? What does the input tell me? Yeah, essentially, what is that? Yeah, so the inputs of our sequence of this function are going to tell us where we fall. And then the outputs are going to be whatever we find at that particular position. So an n value or an input of 3, f of 3 would tell us that we are looking at the third position in our sequence. So going over there and looking. And yes, we can refer to our sequence with this kind of function notation, f of 1 equals -4. More often than not, though, you will see instead the subscript notation, the sequence notation, where we will indicate the input to our function with this index. So a sub 1 means that when our input is 1, when we are looking at the first position of our sequence, then what we find there will be 4. This particular case, or I guess -4 would be more accurate. All right, to that end, we also talked about a couple of specifics. So if I want to refer to a generic term here, I would use a sub n. And then just a reminder that if I am referring to a sub n minus 1, then I am referring to the term that came immediately before that sequence, that particular term. So if I want to talk about a sub 7, then I might reference something to do with the term that came before. That would be a sub 6. If I want to talk about what comes after a sub n plus 1 for a sub 7, that would be like a sub 8. Notice that I am not subtracting 1 from the actual value that I find there. I am simply moving to the left or to the right by, in this case, by 1. All right. Now, we said that we were going to really only be focusing on sequences that had patterns. Then we were a little bit more narrow with that definition, these multiplication patterns, these addition patterns. And that was very, very deliberate. The main issue that I have with the sequences that are on the board, nothing that's, their fault at all. But if I want to make some kind of inference, if I want to figure out what's going on in the sequence beyond what is just given to me here, I'm going to have a very, very difficult time doing it when there is no pattern. By difficult, I mean it's impossible. I can't make a guess as to what a sub 5 is going to be for these sequences because there is no rhyme or reason to why the terms are the way that they are. Whereas if we have a much more predictable pattern, there should be a way to instead maybe categorize that movement that we see, that ability to move from one term to the next. All right, so we are going to start by looking at two different ways that we can define our sequences. One is kind of the heart of what is going on with sequences when we are referring to sequences. And then the other is more of kind of a taking that thing that we got, the heart of our sequences, and then making it useful. Because as it is when we first derive it, it is not going to be all that nice to play with. We're going to start with looking at what is called the recursive form for our sequence here. So I want to consider the sequence that is 4, 2, 0, negative 2, so on. This is the sequence that we looked at for 1a here. When we were looking at this sequence, what did we kind of note here? Okay, we're subtracting 2. So the pattern that we have to follow is that we take the term that came before and we subtract 2. Now, recursion as a concept, as an idea, is one that you'll often see in, say, something like computer science. The idea is we are going to use previous outputs as our new inputs. So what was an output from like the previous step is going to become the input for our new step here. For instance, if I wanted to communicate that the way I move from my third term to my second term is by subtracting 2, I might say something along the lines of a sub 4 is equal to the term that came before it, a sub 3, minus 2. And this would be recursive. I am taking a former output, a sub 3, and I am modifying it to take me to my next output. All right. Now, obviously, that is very, very specific. Let's maybe generalize this. We know that our arithmetic sequence, this step of how I move from one term to the next, should be the same regardless of what step I am on. And so how might I formulate the recursive step that would get me to a sub n? So for any random term in my sequence, how do I get there? Pin in that, we're going to get there. Not there yet. That's jumping ahead a little bit. I just mean at the very, very bare bones of like what we just did, how do I get to any random term in my sequence? A sub n minus 1, and what am I doing to a sub n minus 1? In this case, we are subtracting 2. Say again. Yeah, whatever that pattern is. So this you are often going to see referred to as the recursive step. And we can really think of it as detailing the pattern that we have to follow. It's how we move from the previous term to the term that we currently care about, in this case, a sub n. Now, is it enough to talk about just the recursive step? Well, sometimes the recursive step is enough to differentiate one sequence from another. For instance, if I were to compare this sequence that I have here with the sequence of 4, 1, -2, -5, it's very, very clear that the difference is the pattern that we are following. For when I'm subtracting 2, for when I'm subtracting -3, giving you this recursive step would be enough for you to say, okay, this is referring to my sequence that's above versus my sequence that's below. But is it always going to be enough? For instance, what if we were to compare my sequence above with the sequence that is 2, 0, -2, -4, so on? Well, first of all, is this new sequence the same as the sequence that I have up there? No, it's not the same. In particular, order matters. Notice that the first term of my first sequence is not the first term of my second sequence. The second term of my second sequence is not the second term of my new sequence, and so on. Okay. But if I gave you that I can find a new term by subtracting 2 from my old term, is that enough to differentiate between these two sequences? I would say no. And I would say no because they have the same what? Pattern. They follow the same pattern. But they are different sequences. And so we're going to need an extra piece of information here in order to differentiate what we see. What could I use that would tell me definitively that I am looking at my top sequence rather than my bottom sequence? So we know how we move. We take the previous term, we subtract 2. But what else do I need to know? Say again? Where we start. I also need to specify, by the way, I'm starting at 4. Right. So think of this as, we'll call this our initial condition. And it's just, where do we start? And notice that in tandem, where we start and how we move perfectly define a sequence, right? If I compare my first sequence and my second sequence here, they start at the same location. So just knowing where they start wouldn't be enough to differentiate the two. But as soon as I look at the pattern, I can see, okay, well, actually, in fact, this recursive form must refer to the sequence above. Likewise, with my first sequence and my third sequence here, they follow the same pattern. So just knowing the recursive step would not be enough. But if I add to that, by the way, we also start at 4, there is only one sequence that follows the pattern that starts at 4, and that is the sequence that we see above. Okay. Of course, we can take this and make it a little bit more generic. So that was the recursive form for a particular sequence. But if I am thinking about for any kind of, we'll call it any kind of arithmetic sequence, what two pieces of information am I always going to need for my recursive form? So the recursive step, in the case of just any generic arithmetic sequence, what pattern am I always going to follow? Say again. So that'll be the second piece of information that we need here. But what pattern do I follow for an arithmetic sequence? It's always plus something. So a sub n minus 1 plus something. And then what else do I need on top of that plus or that recursive step? Where I start, a sub 1. 2 lines. There's one equation, it's 2 lines. First line tells us how we move. Second line tells us where we start. Technically, it wouldn't need to be where you start. If you define any of your terms, it would work as well. Generally speaking, we'll be defining where we start a sub 1. Right. But worth noting, if I told you that a sub 2 was 2, you can kind of work backwards to figure out what a sub 1 would need to be, and then it also works well. It defines it perfectly well as well. But this is kind of what we say is what we're looking for. Okay, so I heard Dylan mention the name for this value of d here. What is this called, Dylan? The common difference. But really, we're just going to think of this as our addition pattern. Like, yeah, we could go into what this d is made up of, but why do that? If we're subtracting 2, we're subtracting 2, d is minus 2. Technically speaking, it's the common difference, because if you take the difference of any 2 consecutive terms, you should always get that common difference. But that should also just make a lot of sense. If I move from a sub n minus 1 to a sub n by adding d, then finding that difference should just be d, right? I've displaced myself by d, and so that difference is just, it's fairly reflexive, fairly recursive, one might even say. But not too worried about that. It's just our addition pattern. For our geometric sequence, we're going to find much the same thing. We need to know where we start. We need to know how we move. Where we start is still just a sub 1, wherever that is. And then how are we moving with a geometric sequence? To get to a sub n, what do I do to the term that came before it? Multiply it by something. And in this case, that's something. We're going to call this the common ratio. But we're just going to think about this as our multiplication pattern, whatever that pattern is that we noticed. Okay, so what is the point of having these? Well, my claim was that the point was now we can talk about just random terms of our sequence, right? We should now, from these, be able to pinpoint exactly what kind of the terms of our sequence are. That being said, as it stands right now, that process is not fun. So for instance, let's consider this sequence that we have here. Let's say that for this sequence, I want to find a sub 7. And the only information that I have to find a sub 7 is the recursive form of my sequence. Right. In order to gain information about a sub 7, what do I need to know information about? Well, we'll eventually need a sub 1. That is certainly true. We'll certainly at some point need the difference, but just by my recursive step here, what must a sub 7 be the same as? In order to make some kind of claim about what a sub 7 is, I need to know what? Yeah, whatever a, but which in this case would be if n is 7. A sub 6, we need to know what a sub 6 is. In particular, a sub 7 is a sub 6 minus 2. But do we know what a sub 6 is? No, no idea. Okay, but that's okay. In order to figure out what a sub 6 is, what could I say a sub 6 is equal to? A sub 5 minus 2? Okay, cool. Do we know anything about a sub 5? No, still don't know anything about that. Okay, but that's fine. What is a sub 5 going to be the same as? A sub 4 minus 2. Okay, cool. Still don't know anything about a sub 4, but a sub 4 is a sub 3 minus 2, which is going to be a sub 2 minus 2, which is going to be a sub 1 minus 2. Now, we do know what's a sub 1. What's a sub 1 here? So a sub 1 is 4. And so now I could plug in, okay, a sub 2 is going to be 2, and a sub 3 is going to be 0, and a sub 4 is going to be negative 2, and a sub 5 is going to be negative 4, and a sub 6 is going to be negative 6, and a sub 7 is going to be negative 8. Okay, we found negative 8. And if I asked you to do that for a sub 100, you should look at me like I'm an absolutely insane person, because that would be utterly ridiculous. So while this does a very good job at defining our sequence, it does not do it in a very efficient manner. It doesn't let us just jump from one step to kind of our final step. It requires us to know every single piece along the way. But what if I want to jump from 1 to the end? If I start at 4 and I end at negative 8, what kind of observation could I have made that would have allowed me to just jump straight to the end here? Well, I would say that we could make 2 observations. How many steps does it require us to go from the first term to the 7th term? How many? How many steps? Not quite 7. 6 steps. So 1, 6 steps from a sub 1 to a sub 7, right? Normally, if we were starting at 0, it would be 7, but in this case, we're starting at 1, so it would be 6. And then what does it mean to take a step? Which in this case is? It's the same as subtracting 2. Maybe rather than is the same as negative 2, we'll say is the same as subtracting 2. So how many times am I going to be subtracting 2 from my initial term? 6 times, which means overall, how much am I going to subtract from my initial term? I'm going to subtract 12. Or in other words, I could find a sub 7 by taking where I start and subtracting, in this case, 2 times 6, subtracting 2 6 times from that initial term. And we get exactly what we see here, we get negative 8. Okay. Again, let's do our best to take this, and let's take this idea and generalize it. This is going to be our explicit form. This is our condensed, this is our slightly more useful way to conceptualize what is going on with our sequence. How can I find any random term within my sequence? For our arithmetics, this is going to be a sub n. So how do I jump from a sub 1 to a sub n? We're going to start at a sub 1, and then how many steps am I going to need to take to get from a sub 1 to a sub n? N minus 1 steps. And taking a step is the same as doing what? For my generic function here, adding the common difference, adding that value of d. Adding d over and over and over again is the same as adding d n minus 1 times. So we'll take the product of those. That repeated addition of d kind of collecting into this multiplication form. All right, so again, just to clarify, this is where we start. This is our number of steps. And we can kind of think of this as like the size of the step. just like what it means to take a step. Right, in this case, taking a step means adding the common difference. How many times are we going to do that? Well, how many steps do we have to take to go from 1 to n minus 1? We can do the exact same thing for our geometric sequence here. Exact same logic, exact same everything. What does it mean to take a step for our geometric sequence? What am I doing to a sub 1? Multiplying by r. How many steps does it take to go from 1 to n? So from like 1 to 100, it would take 99, so it'll be n minus 1, okay? And then what does it mean to do this multiplication of r? How would I communicate that I want to multiply by r a whole bunch of times? How would I show that? Raise it to the power of n minus 1. Again, exact same idea. Where we start, the number of steps that we take, and the size, or what it means to take a step. Which just basically lets us shortcut to the very end. Yeah, Dylan. Yeah, they let us jump to the end without needing to know all of the little mini bits that kind of fall in the middle, right? To figure out a sub n for my recursive form, I would need to know a sub n minus 1, which would require me to know a sub n minus 2. And at that point, it becomes a massive hassle. And this is just saying, for very specifically arithmetic and geometric sequences, again, very specifically, that I know what a step is. I know how many I'm going to take. Let's just take them all at once and see where we end up. Now, this condensed version is very, very nice for our arithmetic and geometric sequences. There are going to be some sequences that are better defined by recursion. Fantastic example would be Fibonacci sequence. So if we're thinking of like 1, 1, 2, 3, 5, 8, so on. Defining this recursively, well, we would need to define the initial condition. I'm taking the two numbers prior and adding them together. So the initial condition here would be that like a sub 1 equals 1 and that a sub 2 is equal to 1. So notice our initial condition here requires us to define two numbers. And then our recursive step is that f of n is the two previous terms added together. It's very, very well defined recursively. Look up the explicit definition for the Fibonacci sequence. It's a mess. It's awful. It's terrible. So not that it doesn't exist, but that sometimes our recursive definition is the most logical way to kind of approach it. It's just in the case of our exponent, or in the case of our geometric and our arithmetics, we have nice, clean ways of kind of consolidating and jumping straight to the end. All right, let's take a stab at example 2a here. So in this case, we are trying to write both the recursive and explicit forms, and then we're going to use the explicit form to find a sub 20, to find the 20th term of our sequence. Now, looking at 2a, we've already done the recursive form for this. What is my start point? Where do I start? Starting at 4. And then how do I take a step? Subtracting 2. Okay. Fantastic. If I'm thinking about my explicit form, if I have a sub n starting at a sub 1, and then what am I doing to a sub 1? So, yeah, exactly. Well, ultimately, when we're looking for a sub 20, that's what we're going to look at. But we're thinking starting at 4 still. What am I doing to 4? The way I'm going to write this is, well, I'm subtracting 2 from 4. And then how many times am I subtracting 2 from 4? Well, it's going to be n minus 1 times. Now, notice here, you could also write 4 plus n minus 1 times negative 2. It's the same thing. Right? I think that this way, how it is written, makes a lot of intuitive sense as to what I'm saying, as just like we're starting at 4, we're subtracting 2. How many times am I subtracting 2? It's going to be n minus 1 times. And then what value of n do I actually care about here, Haddon? When n is equal to 20, we are taking 4, we are subtracting 2 19 times. And so I get negative 34. Questions here with our recursive form, explicit form, using the explicit form to find particular values of a sub n. Sure, you could use the recursive. It would require, so like to know something about a sub 20, I would need to know a sub 19. To know something about a sub 19, I would need to know something about a sub 18. It would take a very, very long time, which is why we are shortcutting it with the explicit form. So you certainly can use the recursive form. I would not recommend using the recursive form for these specifically. Not that there's like anything wrong with it, it's just slow. It's just slow. Yeah. That's an A. That's an A. Yeah. Other questions? All right. Then let us take a stab at B, C, and D. I would take special note to be careful of whether you're working with an arithmetic or a geometric sequence, as those do have very different formulas, but keeping that idea together of where do I start, how many steps am I going to take, what does it mean to take a step? Am I adding by a common difference? Am I multiplying by a common ratio? How many times am I doing that? What does that look like to do that over and over and over again? So, so what do I do? Dividing by 2 or multiplying by. Yeah. So to go to a sub n, I would take the term that came before it, a sub n minus 1, and multiply it by 1/2. Just for our recursive definitions. And thinking, well, that's going to be that a sub 1 times r to the n minus 1 plus r and r. Yes, so this would be your recursive. And then this would be your, it would be your explicit after you've evaluated it. And then if you want the explicit form just in general, you'd replace this with an n and this with an m. Yes, and then that's workers. And so that's okay. Yeah.
We don't have to simplify.
Not only do you not need to, you should not, because you're going to do decimal approximation, and it's just better to leave the equivalent.
Okay. Should we do that for all?
Basically, right? Yes.
Basically.
Okay. What am I doing to what am I doing to a sub 1 over and over and over? Okay, so I'm dividing by 2 or multiplying by 1/2. Is this what we're saying? Are we saying that we're taking 8 and multiplying it by 1/2 over and over and over again? That we're doing with it here. We're adding. Okay, so how could we adjust that to account for the fact that I'm multiplying rather than? So we're going to do 8 times 1/2, and then how many times are we going to multiply by 1/2? 20 minus 1, n minus 1 times, right? And then multiplying by 1/2 over and over and over again. How do I communicate that? I'm going to multiply by like 2, 5 times. How would I write that? With an exponent. So 1/2, 2 to the power of. This looks good. Just a quick note for the, if you're, I'm asking to write the explicit form, you would want to do it with ends, but yeah, that's fine. And you should just. I want you to not round. I want you to write it as the exact answer. So there's like the 8 over or 8 times 1 over 2 to the just circling answer. Yes. Okay. So where do we start? How do we move it? Divided by 2 or multiplying by 1/2. Cool. So that gives us our recursive form right there. So the first line is just going to be a sub 1 equals 8 to start. And then the second line is going to be that we take our previous term, a sub n minus 1, and multiply it by 1/2 to get a sub n. So a sub n is equal to, and you got it, perfect. A sub n is equal to that previous term, a sub n minus 1. Okay, times 1/2. Awesome. Yeah, that's perfect. So that's recursive. And then explicit is saying, well, I take my a sub 1, and I'm multiplying it by 1/2. And how many times am I going to do that to go from 1 to? So like how many times do I do it to go from 1 to 100? Just if I start at 1 and end at 9. So it'll be to the power of n minus 1. So 8, where we started, what we do, and then how many times we do it. It's going to be whatever n is, n minus 1 times. Yep, exactly. Because we're multiplying over and over and over again. It's the same. It's not crazy. And it's, yeah, it's, yes, and you could just think about that. So dividing by 2 is the same as, okay. So this looks correct, but then repeatedly divided by 2, how do we communicate repeated multiplication of division? So if I was to multiply by 2 over and over and over again, you would use like a power. So this n minus 1 just goes into the power again. Same here, the n minus 1 here is it's -3 to the power of n minus 1. And then this would be plus. It's minus up here because I'm subtracting 2, but it would be a plus down there because we're adding x. So what am I doing to go from one term to the next? What am I doing to go from one number to the next? So if we're going the other way, right? We're starting here and going this way. So if I'm starting here and going this way, I am dividing by 2 or multiplying by 1/2. I'm cutting in half each time. Well, so we're looking at here, right? So we start in 8. How do I go from 8 to 4? Sure, divided by 2, 4 to 2. Well, it also dividing by 2. So we're dividing by 2 over and over and over and over again. And so we're going to take this a sub you divide it by 2, or you can multiply it by 1. These are only. So this is -2 because we're taking our term and so we're adding everything. Or we're subtracting 2. Okay. So adding -2 or subtracting 2. That's why this is -2. Here we're dividing by 2 or multiplying by 1/2. So it's multiplied. It's because it's geometry, so we're multiplying by something rather than adding. Yeah, that looks good for recursive. And then if I am repeatedly multiplying by something over and over and over and over again, how do I communicate that? So think like 2 times 2 times 2 times 2 times 2. How do I like condense that all into like one expression? Yeah, it's going to be the power. So this would be 1/2. And where is this 19 going to go? I'm multiplying by 1/2 19 times. It's going to go into the exponent area. 1/2 of the power of 19. So similarly, okay, so this would be our recursive step here. The recursive formula is basically just this. So a sub n minus 1, sorry, a sub 1 times r n minus 1. So this is like if we did it once, but then we're just saying, okay, well, a sub n minus 1, we're really just doing it a whole bunch of times. Yeah, and then you would plug in like what is a sub 1, a sub 1 is a, r is what happened after your formula, and then this is like what's in it. Yes, and just leave it like that. Because this is, one, it's not quite right because of how you're missing the 10 to the negative bit. But then also, this is just a more precise answer for precise answers. Yeah, that looks good. And then just to be like super, it's not going to matter here. But we do want to make sure that that 19 hits that at -3. Because if it outside, yeah, so it would be -3 outside to the power of 19. Just because if it were an even number, that -3 would become positive.
3 to the power of 19. Right?
Yeah. Otherwise, you're doing the power first. Right. Okay. Yeah, exactly. Which I'll make a point of, especially when we do the series formula here in a second, because that one actually can be very confusing of like where the negative is, and it's very important too, which is kind of like hate it when it's confusing and important. All right. So let's take a look here at 2a. For our recursive form, 2 lines. First line is always where do we start? Second line is always how we move. So where do I start for b here? Sorry, 2b. Starting at 8, so a sub 1 is equal to 8. And then how do I move from one term to the next? multiplying by 1/2. I like multiplying by, you could do dividing by 2, but I think letting the R value be 1/2 is just a little bit, it makes things a little bit cleaner. All right. So let's try doing that all at once. So a sub n, again, we are starting at 8. And what am I doing to that 8? I'm multiplying by 1/2. And then how many times am I multiplying by 1/2? N minus 1. And how do I communicate that I'm multiplying something repeatedly by n minus 1 times? Put it in the power. So to the 1/2, how many times to the 1/2? N minus 1 times. Okay, but we are looking for a specific value in particular. We're saying, well, what is a sub 20? This is 8 times 1/2 to the 19. And yes, we could plug that into our calculator and get something, but it's actually perfect the way it is. Just leave it like that. Try not to round if you can avoid it. So 8 times 1/2 to the 19. This is less work, which is great. We love less work. And it is more accurate than what you would get if you were to plug into a calculator and round. So just leave it as is. All right, what about for C? What is our, well, first of all, is this an arithmetic or a geometric sequence? This is arithmetic. What am I adding each time? I'm adding an x. So I start where? At x. And then how do I move? Plus x. A sub n minus 1 plus x to get to my next term. And so for a sub n, I get x plus, what am I doing to x? Well, I'm adding x n minus 1 times. And again, if you have this reversed, if it's x plus n minus 1 times x, it's the exact same thing. I just, so that the verbalization is consistent with what we are seeing here. I'm writing it like this, and then a sub 20, I get that this is x plus 19x, which is just 20x. All right, one last one. Where do I start? How do I move? Start at 1, and how do I move? Multiply by -3, so a sub n minus 1 times -3. So in this case, a sub n equal to, starting at 1, what am I doing to 1? Multiplying by -3, and how many times am I going to do it? N minus 1 times, which for a sub 20 is going to be 1 times -3 to the 19, which is like 1.1 something billion, blah, 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 blah. But also, this is perfectly fine. I would be more than happy to take this. What does n represent? Yeah, that's like the term of, that's our input, right? It's the term of the sequence. It's where we fall in the list. And so if I have something raised to the n, what kind of function am I looking at? Yeah, it's an exponential function. It's like what we've been doing with like 2 to the x, 5 to the x, so on and so forth. Now that makes a lot of sense with b, right? 1/2 to the power of n makes a ton of sense. D is a little bit weird though, because when we were first doing our exponentials, we spent like 10, 15 minutes talking about like restrictions that we have to put on A and B, those values there that we had to put. And what was one of the restrictions? What are we not allowed to have as a base? It's like really actually one of the only restrictions from 3.1. Yeah, we couldn't have negative bases. Does anyone remember why we weren't allowed to have a negative base? What was the issue with negative 2 to the power of x? Okay, so that's okay. So to the power of 2, we do get a positive number. That's okay, though. Positive number is fine. But there is a particular value of x that we want to be very, very careful of. Actually, there are a particular set of values of x that we want to be very, very particular of. So we're in the right area. 3, we'd still get negative 8, which is okay. We're fine with negative 8. Where do we run into problems? Fractions. Because what is negative 2 to the 1/2? The square root of negative 2. And am I allowed to take the square root of a negative? No. So I'm not allowed, if I have a negative base, to plug in fractions for my input. Is that something that we have to worry about with our sequence? No. Yeah, we're always plugging in natural numbers into our sequence. So we're never going to have to worry about accidentally plugging in a fraction, accidentally taking the square root of a negative. That's okay. So it's not that something is like fundamentally changed. It's not that like all of a sudden our bases are now allowed to be negative, but because we don't have to worry about plugging in fractions, it is in fact okay for our bases to be negative here. It doesn't break anything. So more of just like an interesting observation here, which is that, hey, we have negative bases for the first time, and we're okay with that, but we're only okay with that because the exponent is never going to be a fraction. It's always going to be a whole number. Because otherwise, we would run into an issue. We would be unhappy. All right, questions with our example 2. All right, one more thing that we are going to look at, and that is our well, we'll get to that here in a moment. Those are our series for our sequences. So a sequence is just the list of numbers. The series is going to be, generally speaking, you see this as like a partial sum, but we are going to define the series as just the sum of the first n terms of our sequence. Right? So no longer are we looking at just what does our list tell us. Now we're saying, well, what happens when I add up a whole bunch of pieces of our list? What does that tell us? Again, we're going to be focusing on what's going on with regards to our, in this case, our arithmetic and geometric series or sequences, kind of taking some of these notions and translating them. A couple of pieces of notation. So you'll often refer to, or when you hear series referred to, you will see that they are denoted with this S sub n. So the sum of the first however many numbers. You will also often see this written in summation notation. So this E looking thing is a sigma, capital Greek S. And you'll be given an index, so maybe from I equals 1 up to n of like all of my a sub i's, which is basically just saying I want to take a sub 1 plus a sub 2 plus a sub 3 all the way up to a sub n. Okay. So again, similarly to our recursive kind of process, if we just had to do this by hand, this would not be very pleasant. This would suck. If I asked you to find S sub 20 of something, you would have to find a sub 1 and a sub 2 and a sub 3 and a sub 4 all the way up to a sub 20, and then you're plugging them into your calculator and you're just tapping away plus a sub 5 plus a sub 6 plus a sub 7 all the way up. Not very fun. So let's see if we can't figure out a way to be very, very clever with our addition so that we could maybe circumvent this process, so that we can cheat a little bit here. I want to consider, let's consider a sequence here. We're going to just consider the sequence of numbers as an arithmetic sequence. You can confirm this for yourself, of just 1, 2, 3, 4, 5, and so on. And I want to know what S sub 100 is. In other words, I want to know the sum of the first 100 numbers. Okay, so we could, in our calculator, 1 plus 2 plus 3 plus 4 plus 5 plus 6, blah, 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 blah. But let's see if we can be a little bit more deliberate than that. Is there a way that I could be very, very particular, very, very clever with my addition to make this problem a lot easier, maybe not easier, but a lot less grueling than just adding 100 numbers together and seeing what I get? Could we be clever with our addition here? Because I can add in any order that I like, but could we be clever with our addition here in such a way that I don't just have to add 100 numbers altogether? And maybe it's a little tricky to see. So let's see if we can't see what happens here. Rather than just doing 1 plus 2 plus 3, blah, 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 I'm actually going to add my first term, a sub 1, plus my last term here, a sub 100. So we're going to be done with that, done with that. What is this total to? 101. Okay. So that's cool. A little bit of deliberate addition there. What will I get if I do the same with my second term and my second from the last term? I will also get 101. Okay, what about my third term and my third to last term? Also going to get 101. How many of these 101 groups can I make? 50. Where'd 50 come from? Yeah, we're adding two numbers together. How many numbers do I have total that I'm going to be adding from? I've got 100. And so we would expect S sub 100 to be the same as, well, this is just going to be 100 over 2, so 50, the number of pairs that I could make, times 1 plus 100, or 101. Yeah, it's like the number of numbers that we're all adding together. We're cutting that in half because that's like the number of pairs that we can create. And then we're multiplying that by the sum of the first and last. Exactly. Yeah, very good. Now, this is obviously, again, very, very specific, but it generalizes exactly as you would expect into just our general arithmetic form. If I want to know what S sub n is, then I can take n over 2 pairs of a sub 1 plus a sub n. of my first and my last term. You can confirm this for yourself. The observation that you would need in order to confirm this for yourself is that a sub 2 is the same as a sub 1 plus the common difference, and that a sub n minus 1 is the same as a sub n minus the common difference. So notice that a sub 2 plus a sub n minus 1, the second term and the second to last term, do in fact add up to be the sum of my first and last terms. And so we get this exact thing. Now, what assumption am I making about n when I'm saying that we can make n over 2 of these pairs? Okay, I'm assuming that n must be even. This only worked because n was 100. We can divide 100 nice in half. The good news for us is that even when n is odd, well, if we think about doing this with like 101, for instance, and we think about, okay, I'm making pairs. In this case, my pairs are adding up to be 102. So 1 plus 101, 2 plus 100, 3 plus 99, so on. They're all adding up to be 102. I get to 50 plus 52. And then what number is right in the middle there of 1 and 101? 51 is right in the middle. The good news is, well, I have n minus 1 over 2 pairs, and then that final number is just the average of 1 and 101. It's just the average of my first and my last. When you add those together, it condenses actually into exactly the same thing that we see here of n over 2 times a sub 1 plus a sub n. And so this works even if n is odd, and you can't do the perfectly pairing thing because the odd duck out is perfectly in the middle of a sub 1 and a sub n anyway. So this will work regardless of what n is, and it gives us this nice condensed way where, think of the information that we needed before in order to find the sum. We needed to know all of those terms in between. Now what do we need to know? Well, it's sufficient just to know what's going on with a sub 1 and a sub n. Which is cool. It requires a lot less information than what we were required before. This is also a really famous ACT problem, also a very famous CLEP test problem, if you're thinking about taking the CLEP test, of like, person is making like seats in the auditorium, and they want to know like how many seats are going to be in their final row. This kind of methodology is going to be very much one that you can kind of use. Okay, so this gives us the sum S sub n for any of our arithmetic series here. This is n over 2 times a sub 1 plus a sub n. There are a couple of different ways to write this. You guys may have seen this as n times a sub 1 plus a sub n all divided by 2. It's the exact same thing. I can do the multiplication and division in any order I like, but this is how I am choosing to write it, to kind of pay homage to the fact that I am making a bunch of these a sub 1 plus a sub n pairs and then adding them all together. All right, we run into the desire for the exact same thing with our geometric sequence. So we're thinking the sum from I equals 1 up to n of a sub I, where this is a sub 1 plus a sub 2 plus a sub n minus 1 plus a sub n. What is a sub 2 the same as? A sub 1, what do I do to a sub 1 for a geometric sequence? Multiply it by whatever r is. So this sum is really the same as like a sub 1 plus, we'll say like a sub 1 times r. And then it would be like plus a sub 1 times like r squared. Okay, and then we could go all the way to the other end. A sub n minus 1 is going to be like a sub 1 times r to the n minus 2. And then a sub n would be like a sub 1 times r to the n minus 1. A little messy there, but good enough. So a sub 1 r to the n minus 2, a sub 1 r to the n minus 1. And so how can we collapse these? Well, it's not going to be quite as easy as just like adding the first and the last terms, nothing like that. We're actually going to require a little bit of clever multiplication here in order to make this collapse. In particular, what I want to do is I'm going to multiply both sides by 1 minus r. We could think of distributing this sum through. We would get s sub n minus r times s sub n. You could distribute that sum. That'd be totally fine. What am I going to end up with? Well, in this case, we'll say 1 minus r times s sub n. All right. 1 times s sub n is just a carbon copy of itself. Right? We get the exact same thing. So this is just a sub 1 plus a sub 1 r plus a sub 1 r squared all the way up to a sub 1 r to the n minus 1. And then multiplying by a negative r. So we're taking a negative r, we're distributing it through. A sub 1 times negative r is negative a sub 1 r. A sub 2 times negative r is negative a sub 1 r squared. On and on and on. A sub 1 r to the n minus 2, that was a sub n minus 1, times r is going to be a sub 1 r to the n minus 1. And then our final term times negative r minus a sub 1 r to the power of n. What was the point of that? What did that cause to happen? Well, what's going to happen to every single one of my annoying middle terms that before I would have had to find? They all cancel. A sub 2 cancels with negative r times a sub 1. A sub 3 cancels with negative r times a sub 2. A sub 4 cancels with negative r times a sub 3. And so the only things that are left are that first term a sub 1 and the very last term that I'm left with after multiplying by negative r, which is negative a sub 1 r to the power of n. All of my middle stuff cancels out here. And just to tidy things up, we could factor out an a sub 1. Okay, so a little bit of clever multiplication forced everything to cancel. We end up with a very, very nice simplified version of what we were looking at before. Okay. But do I care about what 1 minus r times my sum is? Not really. What am I ultimately looking for? My sum. How would I solve for my sum here? Divide both sides by 1 minus r. And so I get that my sum is equal to a sub 1 times 1 minus r to the n, all divided by 1 minus r. So s sub n, a sub 1 times 1 minus r to the n, all divided by 1 minus r. Which ultimately is the thing that we were looking for, a much, much, much less complicated process than finding every single term in between 1 and 20, or 1 and 100, or 1 and 1,000, and adding them together. All right. So let's take a look at example 3. We're trying to find the sum of the first 20 terms of our sequence. Now for A, we've looked at this one a lot. Is this an arithmetic or a geometric sequence? This is arithmetic. And so we know that S sub 20 should be equal to, how many pairs am I able to make from 20? 10, so that's 20 over 2. And then each pair is A sub 1, which is 4, and then A sub n, or A sub 20, which we found earlier to be negative 34. Ten times negative 30, I get negative 300. Well, this is just the formula. So we were using our formula that we derived, n over 2, so number of pairs that I can make, times 1 plus a sub n, so the sum of my first and my last term, is my sum of my whole thing.
No, but for like a of n, you're only able to.
So would we have to do like this process up here to find a sub n?
Yeah.
Yes. Yeah, you would need to, you'd probably in this be asked to find a sub 20. You'd need to first find a sub 20, which we already did, and then plug it into this formula. So I'm using kind of prior knowledge here, but yes, you would normally need to find a sub 20 here. Yeah, good question. So actually the bulk of this problem is in this right here. All right, we can do the exact same thing for D here. In this case, is our function arithmetic or geometric? Geometric. So S sub 20 is going to be equal to A sub 1, which is just 1, times 1 minus R. What is my R here? What am I multiplying by? Negative 3. So 1 minus, be very, very careful here. Negative 3 to the power of 20. And then what am I dividing by? 1 minus R? Minus negative 3. Be very, 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 very careful here. This is exactly what it needs to look like. Notice that I'm taking negative 3 and I am first raising it to the power of 20 and then I am subtracting it. Why is that so important? Well, negative 3 to the power of 20 is going to be what kind of number? It's a positive number. And when I am then subtracting it, 1 minus a really big positive number, I'm going to end up with a negative number. So we need to be very, 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 very careful about how we are setting this up so that we are doing it in such a way that when I evaluate what's going on in my numerator, that my negatives and positives end up working properly. For instance, would I be able to, like down here, 1 minus negative 3 is the same as 1 plus 3. Can I do the same thing up here? Can I say that this is 1 plus 3 to the 20? No, I cannot. I first have to apply my squared, and my squared is going to make the negative go away, at which point I just end up with 1 minus 3 to the 20. All right. So being very, very, very careful with our parentheses and our powers here. And this is like 800 million, negative 800 million something. But again, you are done here. This is perfect. Sure, why not? Yeah, I don't mind. You can just totally leave that as is. All right, questions?
What's the formula for the geometric series again?
So geometric was what we see here. So the one above is the arithmetic, the one below is the geometric. R is the ratio, the thing that's our multiplication pattern. The thing that we are multiplying by in order to move from one step to the next.
Like the A, because it said like
Yeah.
-3.
Yeah.
It's just like another word for AN.
It's another word for the multiplication pattern. So A sub n is like what we find inside of our, so like A sub, if we're looking here, A sub 3 would be 9. A sub 2 would be -3. A sub 4 would be -27. It's the actual numbers that we see. And the way we move from one number to the next is multiplying by -3. So A sub whatever is just the term that fits at that particular value.
Arithmetic, then we use the beginning radical, but if it's this, we use as the radius.
No, not the radius. It is just the multiplication pattern. The thing that we multiply by to go from one step to the next.
That's what R is.
That's all. Yeah.
That's all for geometric.
That's just for geometric. If it's the arithmetic, then we use that D, that common difference, but it serves the same purpose. It's what we add in order to move from one step to the next. R is what we multiply by, D is what we add. And ultimately, they're the same thing other than that. It's just the pattern that we follow.
I'm just making sure because we got A and then -3 from the last thing.
So for the last one,
It says -3.
so A sub n, the formula is -3 to the power of n minus 1, where the -3 that we see here is that R. Yes. But it's R to a power. Okay, before we are done, I need you guys to get out your computers and go to Schoology. In the Unit 3 folder, there is an exit ticket for you all to complete. Tomorrow is going to be a review day for the test. Take a moment to let me know what you would like to see for the review day tomorrow. Yes, Simran. All